Hello! Today we'll be observing a truly sad specimen, a student taking a physics exam. We can see from her expression that she's feeling well prepared. Here comes our predator, the physics exam. Watch as she reads the instruction page. Here we find our first example of biophysics. Right now, light is entering the room and the paper is reflecting light into her eye. Once light enters the eye, it goes through the cornea, which is located in the front part of the eye. The cornea bends the light and refracts it to the retina, which is located on the back of the eye. You may be wondering what it means for the light to refract. Refraction is the bending of light caused by two mismatched refractive indexes between two mediums. In this case, the two mediums would be referring to the inside and the outside of the eye. We can use Snell's law to compare the relations of the refraction between two mediums. Snell's law can be simply written as shown, where theta 1 is the angle of incidence, or approaching the cornea. Theta 2 is the angle of refraction, or the angle of light after it hits the cornea, and n, which is a unitless measurement called the refractive index. We could find the angle of refraction if we know the angle of the light approaching the cornea, and both the refractive indexes of the atmosphere and inside the cornea. For instance, say a ray of light is coming toward the cornea at an angle of incidence of 45 degrees. If the refractive index of the cornea is 1.388 and the refractive index of the air is 1.000293, what is the angle of refraction after the light hits the cornea?
Snell's law can be rearranged as shown, and then our numbers can be plugged in with the inverse sign of 1.000293 over 1.388 times the sine of 45 degrees, which gives us the angle of refraction after the light enters the cornea as 30.64 degrees.
That barely scratches the surface of what biophysicists can study. The eye is extremely complicated. For example, these scientists are studying the detection of light by photoreceptors. Photoreceptors are within the retina, which includes rods and cones. There are many aspects of physics involved, including light, energy, chemical gradients, and so forth. All of these concepts work together to allow the student to read the test. Look at the way her hand moves as she answers the first question. We could feel the tension in the air, but did you know there is also tension in her muscles? The tension in your muscles is what allows you to pick things up. Did you know that your muscles contract and never expand beyond resting point? This can be supported through biophysics using a simple experiment about tension. An individual muscle fiber was stretched to varying lengths, and its tension was measured on each length. Each fiber has a thick and thin filament that work together to contract the muscle. This experiment hopes to show the relation between these filaments, but it also shows that muscles cannot expand beyond resting point because when they do, the tension drops to zero. The tension increases as the muscle is stretched up until the resting length. This broader physiological application of this biophysical experiment supports the sliding filament theory. Let's go back to our student who is now approaching question 3.
A penguin with a mass of 8 kilograms curls up into a ball. Oh crap, why didn't I pay more attention to that YouTube video?
Oh no, it looks like she doesn't know the answer to this problem. See, now look, she's hyperventilating. This is actually a very interesting biophysical phenomenon. Let's take a closer look. In breathing, inspiration means that air moves into the lungs. This actually follows Boyle's law closely. When the chest cavity is enlarged, the pressure drops. According to Boyle's law, the volume is inversely proportional to the pressure. On the other hand, expiration means air moves out of lungs. This also follows Boyle's law. A decrease in volume size increases the pressure. Air flows out of the lungs until the alveolar pressure equals the pressure of the atmosphere. Your lungs hold a certain amount of air called dead space. This can be found within the air passageways towards alveoli in your lungs. The total volume of dead space holds about 150 milliliters of air in a normal adult. In this space, there is no exchange in gases with the blood. The air in the dead space has already exchanged gases with the blood in the previous inspiration. The dead space is usually the first volume of old air left from the preceding expiration. Each time your lungs undergo inspiration, the air in the dead space is quickly replaced with air that has already had gas exchanged. The alveolar ventilation measures the amount of new, fresh air from the atmosphere that reaches the alveoli per minute. Hyperventilation occurs when you are not breathing deep enough to get fresh air to enter from the atmosphere. In physics, what's happening is that your lungs volume is not expanding enough to lower the pressure enough to create suction in the alveoli. The amount of fresh air you breathe into, which is the tidal volume, is approximately equal to the amount of your dead space volume. Therefore, tidal volume, or the volume of air entering your lungs, minus the dead space volume, which is usually 150 milliliters, equals a very low volume of air the alveoli ventilates per minute. This is why you have a large chance of passing out. You are not getting enough fresh oxygen to the alveoli in your lungs, therefore have less gas exchange. So to avoid hyperventilating, this student should be taking slow, deep breaths so she doesn't pass out. There are other research papers out there that had studied the biophysics of breathing, including this one here, that talks about the lungs' properties of lung surfactant, which can be found on the surface of the lungs. Look at her now as she approaches the end of the test. It's taken its toll on her psyche, and she is beginning to panic on her grades. Panic can increase your sympathetic innervations in your body, and as a result, can increase the constriction of your blood vessels throughout your body. As the vessels constrict, the radius of the vessels gets smaller, and so the total peripheral resistance, or the amount of friction blood encounters, increases. The peripheral resistance follows Poiseuille's law. This law relates vessel length, viscosity, and radius. Assuming the length of the blood vessels and the viscosity of blood are constant, then as the radius decreases, the resistance is increased. The flow of blood can be related back to the pressure using the following equation, combining resistance and pressure. Since the pressure is inversely proportional to the resistance, when your blood vessels contract, your blood pressure increases. There are a lot of other applications of biophysics in the blood, such as looking at the heart's contractility and looking at the cardiac cycle, which relates pressure and volume of your ventricles. Oh, she's finished the test. We hope we've given you a brief introduction to all the possibilities of biophysics. Biophysics is a very complex field which combines elements of physics, biology, biochemistry, physiology, and other disciplines. The possibilities are endless. Go see for yourself.
Hey, Kelly, the physics grades are out.
Oh my gosh.
What'd you get? Are you okay?
Tune in next week for our special episode, The Physics of Freefall.